4 different organic molecule. What I change? I have replaced 1 hydrogen by methyl. Here I have replaced 2 hydrogen by methyl. Here I have replaced all 3 hydrogen by methyl. And you know this is alpha. Here it is alpha carbon. Here it is alpha carbon. Here it is alpha carbon. And alpha hydrogen will show the hyperconjugation, which will reduces this bond length, which will increases this bond length. Now let it is W. This is X. This is Y. This is Z. And let it is P. This is Q. This is R. This is S. Now, if I ask you W, X, Y, Z, that is the length between the alpha carbon and the sp2 hybridized carbon. Do compare their length. How do you will compare it? Hyperconjugation will help you. Dear students, today we will learn about hyperconjugation, which is the most important part of general organic chemistry. Prior to that, to get better digestion, we will discuss first overall GOC, general organic chemistry. What part of organic chemistry we will discuss in GOC, and what idea you will get from general organic chemistry, that I am going to discuss. You know, the important part of general organic chemistry, first is inductive effect, second one is hyperconjugation, and the third one is resonance. And what idea you will get from this GOC part, that you have to know first. Actually, an organic molecule or inorganic molecule, I am going to periodic property chapter, you know, Pauling scale of electronegativity. From that you will get idea about inductive. There is a molecule A2, and you know, there you will get bond AA bond. It is a purely covalent bond, since you know the 2 atoms are same here. And its bond energy let DAA, and this bond energy you will get by doing experiment. This is not theoretical. Say another molecule B2, and there also you will get pure covalent bond B, single bond B, since both are same atom. You know, homonuclear diatomic molecules are purely covalent. You can take it is H2, you can take it is F2. Now this bond energy DBB, this is also you will get by doing experiment. Now if A and B form any compound, like in place of A you can consider it is H2, or H, B you can take Cl2. Now H and Cl you know able to form a compound, you know HCl. Like if A bond B, now think you have no idea about electronegativity. Now this bond energy, theoretically, mathematics will tell you that bond energy, if I do consider this is also a pure covalent bond, then its energy should equals to the geometric mean of DAA and DBB. But when you will do experiment, and if you do calculate the bond energy of AB, what you will see? Its bond energy greater than theoretically calculated bond energy. Now, why? That answer you will get from general organic chemistry, or concept of electronegativity, or concept of inductive effect. Actually, you know, bond energy has no sign. When a bond will form, an amount of energy released. When you want to break the bond, that similar amount of energy you have to supply. And you know, we will use IUPAC convention of energy. That means if energy released, then the sign will be the negative, and if energy required, that is sign is positive. That means, for example, theoretically calculated value of AB bond energy, let it is 100 kilojoule per mole. And if you do experiment, practically you got 110 kilojoule per mole. That means, actually, really, when A will form a bond with B, then 100 kilojoule per mole energy released. But it is theoretically should 100 kilojoule. That means AB bond more stable than theoretically calculated stability. Since you know more energy released, more stable bond. Now, why this energy more than calculated? That error, that is 10 kilojoule, I have taken example, 110 experiment, 100 is theory. The 10 difference is explained by GOC or inductive or electronegativity difference. That I am going to explain why this energy difference will arise. Since A atom and B atoms are different. Different means their nucleus are different. Their electronegativity or attraction power towards electrons are different. If I do consider effective nuclear charge of the nucleus of B more than A, then this electron cloud are not symmetrically distributed among the two nucleus A and B. The electron cloud slightly polarized towards the nucleus of B, then it will get some negatively charged. There will get some more accumulation of electron towards the B. Since it is more electronegative, since it has more withdrawing power, and it will get delta positive since electrons are away from A towards the B. That means between atom A and B, apart from covalent relation, apart from electron cloud mixing, there is a dipole-dipole attraction additional, which is additional dipole-dipole attraction. This additional dipole-dipole attraction increases the bond energy, which is not, you will not predicted from the structure if you have not idea about the electronegativity. This is actually inductive. Inductive is nothing but polarization of electron through the sigma bond, which will make the bond is polar, which will make more additional electrostatic attraction between the atom, and it will give additional stability of the molecule. But in chemistry, remember, this is electrostatic. I am going to give a data, see the data and feel the actual thought, actual concept. Delta plus and delta minus. Actually, organic chemistry and chemistry majorly controlled by covalency. Now I will give idea about what is covalency and what is electrostatic. The electrostatic force you can easily understand, plus minus force Coulomb's law, and covalence is different thing. Covalency arises due to overlap of orbital, and you know covalent bond is a directional bond, but electrostatic attraction is a non-directional. I am going to give some data, from that you will get better idea. A plus charge, a minus charge, strong electrostatic attraction, its energy near about 250 kilojoule per mole. Whereas a plus charge, ion dipole attraction and delta minus, you can take this is minus delta plus, its energy reduces to 15 kilojoule per mole. Whereas both is dipole, delta plus and delta minus. Its attraction value near about 1 to 2 kilojoule per mole. That is inductive, I told you. Additional dipole-dipole attraction, that will give more energy, 1 to 2 kilojoule per mole. Now, you know, a carbon-carbon sigma bond, here no electrostatic. Effective charge is 0, both carbon. No electrostatic, only overlap of orbital, which will give energy near about 380 kilojoule per mole. Near about 380 kilojoule per mole, which is greater than simple electrostatic attraction plus minus 250. Only covalence will give this energy. See the point. That means covalence is highly important. That will give much more stability. Whereas C double bond C bond energy will get near about 600 kilojoule per mole. Although there are no electrostatic force of attraction. That means when covalent interaction will occur, its corresponding effect is much more better than inductive or dipole-dipole attraction. That I want to say you. Actually, in the GOC part, GOC part, first is inductive. That inductive about the dipole-dipole interaction, and its corresponding energy is too much less, 1 to 2 kilojoule per mole. Whereas the other two effect, hyperconjugation and resonance, there will get additional covalent interaction, and its corresponding energy is much more greater than inductive. That's why when an organic molecule, there is an inductive, hyperconjugation and resonance will give always priority on resonance and then hyperconjugation, and lastly will give priority on inductive. Today I'll discuss about hyperconjugation, which is additional bonding interaction, additional covalent interaction, and you know additional covalent interaction is nothing but pi interaction. Now I am taking an example. See, I am going to take an example, that is propene. This is propene structure, you know. This is CH double bond CH2, and this carbon, you know, is called alpha carbon. Alpha carbon, you know, this is sp2 hybridized carbon, and the carbon which is directly bonded with sp2, that is called alpha carbon, and these hydrogens are called alpha hydrogen. Actually, hyperconjugation effect shown by alpha hydrogen, and hyperconjugation effect you will get in 3 different systems. One of them is alkene. First I am going to discuss how it will operate in alkene. This is CH bond. Actually, this interaction, if you go to molecular orbital theory and the axis is energy, you know, for this bond there will get 2 molecular orbital. One is sigma bonding MO, another one is sigma anti-bonding MO. And bonding MO energy is less and anti-bonding is higher, you know. No electrons try to reside in anti-bonding MO. This is vacant. And here you will get pi bonding MO and pi anti-bonding MO. Pi bond, you know, weaker than sigma. That's why it is higher energy, and pi anti-bonding also lower than sigma anti-bonding. Actually, this interaction is hyperconjugation. What is hyperconjugation? Sigma CH bonding with pi anti-bonding of C double bond C. This additional interaction is hyperconjugation in alkene. That is not shown in this structure, which is not observed in the structure. This additional bond already present in this propene, and which will give additional stability. Now, schematically, how we will show this hyperconjugation effect? I'll take this structure, that is propene, and I told you the additional bonding interaction, that is pi interaction, where sigma CH will attack to pi anti-bonding of CO, and I am giving the reversible sign H, C, H, and this hydrogen will break as H plus, and this is CH single bond CH2 minus. See, now this minus is not enough stable. That's why H plus never reach to this carbon. Actually, this will take some time, and its lifetime less than this time taken by H plus. That's why that it will immediate reverse back to this structure. Now, what idea you got from this? Similarly, this hydrogen also will show hyperconjugation. This hydrogen also will show hyperconjugation. If I take this structure, then this is perfectly double bond, and its length equivalent to C double bond C. But if you do experiment, what you will see? You will see its length slightly more than C double bond C. Why? Due to this structure contribution, it has some lifetime, it has some contribution, and where you will get here single bond. If I take this is carbon number 1, this is 2, this is 3, this is 1, this is 2, this is 3. That means between C1 C2 there are not 100% double bond. A little bit contribution, there is a single bond. That's why its length experimentally you will get more than C double bond C. Parallelly, this C2 C3 bond length, if you take from this structure, it is perfectly sigma. But if you do experiment, what you will see? The length between C2 and C3 slightly less than carbon-carbon sigma bond. Why this less? Due to this contribution of this hyperconjugative structure. Although it has no reality, it has no direct evidence, it is hypothetical, but indirect evidence, indirect bond length measurement will tell you this is the correct explanation. This is not perfect sigma, it has little bit multiple character, it is not perfectly double bond, it has little bit single bond character. That's why the experimentally observed bond length between C1, C2 greater than C double bond C and C2, C3 less than C single bond C. Another important point you will get from this structure, that is, if I do consider inductive, CH3 will show plus I effect, and which will make it is more electron density. Here the electron density less. But experiment will tell you the electron density on C1 more than C2. How? Due to contribution of this structure, the sigma CH will donate electron to the rest part of the organic compound, and which will increases the electron density of the pi bond, especially it will increases on C1. The electron density on C1 more. If electrophile will come, it will attack on C1 majorly, not on C2. And this will give a clear picture about the electrophilic addition reaction. Since this hyperconjugation sigma CH will increases the electron density of the pi bond, and if electron density of the pi bond increases, then rate of reaction towards electrophile increases. And another important point, last point, hyperconjugation finally explain the hydrogen atom. It has inbuilt polarity, that is due to electronegativity difference. But what you will see, this hydrogen more acidic than its inbuilt polarity due to this hyperconjugative interaction, which will make H as H plus. That means hyperconjugation, what idea you will get from the hyperconjugation? Its actual stability more than theoretically calculated stability due to additional bonding interaction sigma CH and pi antibonding of C double bond C. Another idea, you got the electron density of the pi bond greater than theoretical or expected due to sigma CH donor. And you got idea electron density increases especially on C1, and also the alpha hydrogen is more acidic than expected. Now I will go to give some example where you will finally explain their stability, their rate of reaction towards electrophile, as well as their stability. C, CH2 double bond CH2, simple. Here no hyperconjugation, no alpha carbon. Take propene, CH3 single bond CH double bond CH2. Here 3 alpha hydrogen, 1 alpha carbon. Take another example, but-2ene. Here you will get 2 alpha carbon and 6 alpha hydrogen, that is 6 hyperconjugation. Here you will get 3 hyperconjugation, here 0 hyperconjugation. That means if I do compare the stability, although here the stability comparison is not actually fit, since their formula different, their number of bonds different, but you can take the electron density of the pi bond. Here no hyperconjugation, electron density as a pi bond, but here due to 3 hyperconjugation, electron density of the pi bond greater than ethylene. Here due to 6 hyperconjugation, electron density greater than this. Now the better comparison, if I take different isomers, see, you know, this is but-1-ene. It's another isomer, but-2-ene. Let it is 1, this is 2. See, these two are position isomers. And here alpha carbon, this one, and there are 2 alpha hydrogen, that is 2 hyperconjugation. And here alpha carbon, this one alpha carbon, this one alpha carbon, and here you will get 6 hyperconjugative interaction. Now, which one more stable? More hyperconjugation, more additional bond, more stability. Then stability 2 greater than 1. Actually, stability factor compare if they are isomer to each other. That means equal number of bonds present in the structure. I am going to give another example. Take a cyclic compound. This is cyclohexene, 1-methyl cyclohexene. This is alpha carbon, this is alpha carbon, this is alpha carbon. And here you will get 3 alpha hydrogen, here 2 alpha hydrogen, here 2 alpha hydrogen, and total 7 hyperconjugation here possible. And if I take another isomer of this, just shift the double bond here, here you will get only 2 alpha carbon and each have 2 alpha hydrogen, and here 4 hyperconjugation. That means these two are isomer to each other, only the position of double bond is different. Here you got 7 hyperconjugation, here 4 hyperconjugation. 7 hyperconjugation, 7 additional bond, it is more stable than 4 hyperconjugation. Sometimes in books you will get endocyclic double bond in the ring, and this is exocyclic double bond. Endocyclic double bond more stable than exocyclic double bond, but it is not always correct. I am going to give another example. Take this one. This is also cyclohexane derivative, and I am taking another isomer of this. Put the double bond in the ring, rest part is same, and count the number of hyperconjugation. This is alpha carbon, here 2 alpha hydrogen, 2 alpha hydrogen, 3, 3. Total 10 hyperconjugation is there. And here 2, 2, 1, 5 hyperconjugation. That means which one more stable? 10 hyperconjugation more stable than 5 hyperconjugation. Here see, here the exocyclic double bond more stable than endocyclic. That means the term is not always correct. Just to compare the stability, just to count the hyperconjugation, number of hyperconjugation. From there you will get idea about the stability of different alkene. Now, I am going to give another applications of this hyperconjugation interaction. Another example I am going to give, from that you will get idea about the application of hyperconjugation. Right here, CH3CH double bond CH2. This is propane. Now take but-1-ene CH double bond CH2. Now take this one, CH3CH double bond CH2. Another example, CH3C CH3 CH double bond CH2. I have taken here 4 different organic molecules. What I change? I have replaced 1 hydrogen by methyl. Here I have replaced 2 hydrogen by methyl. Here I have replaced all 3 hydrogen by methyl. And you know this is alpha. Here it is alpha carbon. Here it is alpha carbon. Here it is alpha carbon. And alpha hydrogen will show the hyperconjugation, which will reduces this bond length, which will increases this bond length. Now let it is W. This is X. This is Y. This is Z. And let it is P. This is Q, this is R, this is S. Now, if I ask you W, X, Y, Z, that is the length between the alpha carbon and the sp2 hybridized carbon. Do compare their length. How do you will compare it? Hyperconjugation will help you. See, here hyperconjugation will reduces this bond length. How many hyperconjugation will reduce this bond length? 3. Here the bond length X reduces by 2 number of hyperconjugation. Here the Y length reduces by 1 hyperconjugation. And here no hyperconjugation. That means maximum reduction of length by getting multiple character by hyperconjugation is W. 3 hyperconjugation will reduces this bond length. That means the order of length W less than X less than Y less than Z. The hyperconjugation will help you to get the correct order of bond length. Similarly, if I do compare P, Q, R, S length, see, you know hyperconjugation will make it single bond. 3 number of hyperconjugation will make it single bond, and when it becomes single bond, its length will increases. The 3 number of hyperconjugation will increases P. 2 number of hyperconjugation will increases Q. 1 hyperconjugation will increase R. 0, no hyperconjugation is there, it is protected double bond more or less. That means maximum increase in P. And if I draw the length, order of length, P greater than Q, greater than R, and greater than S. Since its increase is maximum by 3 number of hyperconjugation. Hyperconjugation always will help you to get the actual order of bond length. If this effect will operate on the system, remember, and also you will get idea about the electron density on a particular carbon. Another part. This is a carbon. Another. Electron density of these 4 carbons are not same. If I mark it, let it is A carbon, that is B carbon, this is C carbon, this is D carbon. Now, you know hyperconjugation will make here minus. 3 number of hyperconjugation will increase the electron density on carbon. 2 number of hyperconjugation will increase the electron density on B carbon. 1 number of hyperconjugation will increase electron density on C carbon. Here no hyperconjugation. That means electron density maximum on A carbon. Electron density on a particular carbon. Where you will get maximum? A greater than B, greater than C, greater than D. And from here you can compare rate of reaction towards electrophile. When an electrophile will come, it will, since here minus charge is maximum, this carbon most tightly attracted towards the more attraction you will get towards the electrophile H+. 3 number of hyperconjugation will make negative charge on this carbon A. 2 number of hyperconjugation will make negative charge on B, and 1 hyperconjugation will make negative charge on C carbon, and no hyperconjugation will make more negative on D. That means more negative charge, more electron density you will get on A, then B, then C, then D. And it will help to predict rate of reaction towards electrophile. When an electrophile will come, like E plus or H plus, you know they are electrophile, they will find electron. Then that electrophile maximum attraction filled by A carbon, since here more negative charge. That's why rate of reaction towards electrophile of this molecule more than this, than this, than this. From there you can compare easily the rate of reaction towards electrophile, and you know the maximum reactions of alkene and alkynes are electrophilic reaction, that is electrophilic addition. And from there you have to compare the rate of reaction. By using hyperconjugation concept, you can do easily compare the rate of reaction towards electrophile. Dear students, today we got idea about hyperconjugation operates in alkene and how you will get idea about the order of bond length, that order may be increasing or decreasing, and also you get idea how we'll do compare the stability of different isomeric alkanes. And the most important part that I have discussed in the last part, that is how you will get order of reaction towards electrophile. Thank you, dear students.